Hello, welcome to my series on Green's theorem. Today we're going to start to derive Green's theorem, and then in the later videos we're going to look at some applications and so on. But let's get started with the derivation. So firstly we have the xy plane, and we have a path here, C, which is the blue line. Okay, and C is in a vector field, P of xy. Now P only points in the x direction, therefore its only component is P of xy, I, where P is just some function, and J and K of course are 0. So what we can do is we can split the curve C between 2 points, A and B, and we get C1. C1 is the part of the curve between A and B, and C2 is part of the curve from B to A, moving in an anti-clockwise direction. So for C1, the y values can be denoted as y1x, and for C2, the y values can be denoted by y2x, and of course these y values are on the curve C. So we can compute the line integral of our vector field with our curve. So we have a closed loop, so line integral looks like that, along C of our vector field P, dotted with dr, where r, of course, is our vector valued function mapping the curve C. So, of course, dr can be split into its differential components of x and y, like so. Okay? So let's carry on with the line integral and see where we get. So this, okay, is equal to the line integral of C of, this time it's just P xy, okay, because we're looking at the I component of the vector field, that's the only component, that's not 0. And then, of course, that's dx, okay, because we take the dot product of the other components of r, so dy and dz, they become 0 because they're multiplied by 0 for the vector. So we just get the x components of both of those. Okay, now we can expand this. So we can take the integral from a to b, okay? A to b, of course, is c1. It's along c1. And so that becomes p of x. But remember, the y values were y1 of x. So p of x becomes p of x y1 x dx. Okay. Then we have to add the second integral from b to a this time. So we get b, a, and then p of x, and this time it's y. This time it's y2 of x because we're on c2. Okay, so we get y2 x, and then another bracket, and that's dx. So we've split this line integral into 2 integrals along the curve c1, and this integral is along the curve c2. Okay, so we can actually join these integrals together and simplify it even further. So this becomes the integral from a to b. Okay, now look carefully, this is from a to b, that's from b to a. Now if we combine these, we have to, if we switch the limits of the integral, it becomes a minus. So we would have to switch this integral for it to become a to b, and that means we get a minus p of xy2x dx. So the total integral becomes p of x y1 of x minus p of x y2 of x. And then, in fact, we have to put that all in brackets and to get dx on the end, like so. Okay, so our line integral we have here has now become this. We've split it into the curves C1 and C2, and we've combined the integrals. Okay. So next we can multiply it out by -1. Okay. We do that because it makes things easier later. Integral from a to b minus, so we just switch them around. That becomes a positive. So we get p of x, y2 of x, and then we minus our p of x, y, 1 of x, dx, okay? That is exactly the same. Okay, so we can do something with our integrand we have here, and this integral becomes still negative integral from a to b, okay? But this becomes p of x, y, but we evaluate this at y equals y 1 of x, and y equals y2 of x, okay? That's exactly the same as saying that minus that, okay? And of course we have dx at the end. Alright, now that becomes negative integral from a to b, but we can actually turn this into an integral using our partial derivatives. So that's integral from a to b, and then we get the integral though from y1 of x to y2 of x, okay? And then we have the partial derivative of p with respect to y, dy, dx. Okay, so what we've done here is we've put a partial derivative in and dy. The dy is cancelled to give us a differential of p. If you integrate a differential, you get p. And of course, p is evaluated at y1 and y2, so that's exactly the same as this integral up here. But we've used a double integral now, okay? And we can write it like this as well. We have p of xy evaluated at y1 of x and y2 of x. Okay, if we get rid of the integrals of between a and b, we can simply have it in this form. Integral from y1 of x to y2 of x of the partial derivative of p dy. Okay? So we've established quite an important principle here. We've shown that p of xy evaluated between y1 and y2 is the same as the integral of this partial derivative. Now, let's look at this graphically. dp by dy. Well, let's say that's a surface, okay, on the xy plane. But look what we're doing. We're taking a double integral of this surface over our region divided by y1 and y2, our region R. So that is basically what we had here at the beginning of the video. So we're pretty much taking a double integral under this surface, dp by dy, around the region defined by y1 and y2. We're basically taking the volume, okay? And dp by dy just happens to be our surface. And of course, the height from the xy plane to our surface is dp by dy. So basically, what we've established is that the line integral we had earlier, okay, that was the integral of p of xy, okay, dx, along our curve C is equal to negative the double integral over our region R. Okay, R is defined by y1 and y2, a and b. We've replaced those integrals with R. Okay, and that's dp by dy, okay, dy dx. Alright, and also you can actually simplify dy dx, and of course y times x gives you an area, so that becomes dA. Alright, so we've actually linked the line integral of our vector field over some curve C with a volume integral under some surface with the same region. Okay, and of course we've just done that for a vector field with only x components. And next we're going to do the exact same problem, but this time the vector field is going to have y components.